Hey guys, here's a video to help you with today's lesson and showing that two triangles are congruent. I know yesterday we talked about using rigid motion to get one triangle to map directly on top of the other, which is one method. I'm going to show you another method which is a little bit more useful when we do our proofs to show that two triangles are congruent. The good news is it's kind of a shortcut, if you will, because you don't have to show every single thing matches up just perfectly. In fact, the first thing we're going to do is show that all you really need are the three sides to match up. Okay, so in this picture, the way I wrote it, I have AB congruent to DE, AB congruent to DE, I have AC congruent to DF, and I have BC congruent to EF. And what I'm trying to say is that's enough information to guarantee that these two triangles are congruent using something we call side, side, side congruence postulate. Okay? This is actually what you would use. This is something you would have in your reason bank like we did when we did the proofs originally. Sometimes you'll just see it abbreviated as SSS for obvious reasons, side, side, side. So if you get to a scenario where you have three sides of one triangle congruent to the corresponding sides of the other triangle, you've got the triangles congruent without having to do anything else. So this is, you'll see these when you see the practice for today, and that's what you're looking for. You're looking for all three. Sometimes, though, they don't give you all three. That's great when they have all three, but sometimes they only give you some pieces, but not all the pieces. So like something like this. Maybe in their picture they give you this, and that's it, A, B, C, D. Okay, and if that's all that's given, so you've got AB congruent to DC, great. You've got BD congruent to CA. But you're missing that third piece, right? In the original picture, we had tick marks for all three pairs of sides. So in this kind of example, there's a little bit of a trick you can do. Hopefully you realize that these two triangles are actually sharing this side, right? So the last pair of sides here, if we were to draw these separately, right? If we were to draw these separately, just as an example. So B, C, D. Notice both of them have segment BC in the triangle. So I know it's going to seem a little obvious. You're like, wait a second, of course they're the same thing. But there's actually a reason for it, and the reason for it is called the reflexive property. So you could actually say that BC is congruent to BC by the reflexive property. It's just a property we use when we want to say something is congruent to itself. Okay, again, I know it seems kind of silly. You're like, it's obvious, it's congruent, but when you're doing a formal proof, it has to have this as its reason. Okay, so now we've got 1, 2, 3 pairs of sides congruent to 1, 2, 3 sides from the other triangle. So the triangles would in fact be congruent. You could conclude triangle ABC is congruent to triangle, let's see, A goes with D, right? So ABC would go to DCB if I matched it up perfectly, and you would say by side, side, side. So whenever you see, especially when you see the triangles connected like that, hopefully this is what jumps to mind is reflexive property to help you get that last piece. Okay? All right, let's put it all together. Let's do one actual proof. Okay? I like these kind of pictures, the little bow tie thing. Let's say this is A, B, C, D, and E, and I'm going to give you AE is congruent to CD. So given AE is congruent to CD, I'm also going to give you that B is the midpoint of AD and EC. And I want you to prove that triangle ABE is congruent to triangle, if I go ABE, I'm going to go DBC. Alright, so if we're going to do our proof, we're going to set it up the same way we used to set it up, with statements and reasons. And we'll start with our given, right? So AE is congruent to CD, and B is the midpoint of AD and sorry, AD and EC. That's given. Alright, so you're looking at that picture and you know you're trying to get these two triangles congruent. The only way we know now to get the triangles congruent is with side, side, side. And the only thing they gave us is one pair of sides. So somehow we need to get other pairs of sides congruent. Well, this B being the midpoint has got to do something for us. What does B being the midpoint of AD actually give us? Right? B has got to be directly in the middle. If B is directly in the middle of A to D, well then doesn't that mean that AB and DB would have to be the same thing? Right? If you were to put numbers on this, if AD was 20, each of these would have to be 10. If AB was 5, then DB would be 5. Right? No matter what, these two things have to be the same. Similarly, if B is the midpoint of EC, well, I guess EB and CB would have to be the same. So you can actually put that in your proof. You can do them separately or together because it'd really be the same reason. So AB is congruent to DB, and CB is congruent to EB. And the reason would be, well, we know what a midpoint is. That's actually the definition of midpoint. Okay? Now look at our picture. We have one pair of sides congruent, two pairs of sides congruent, three pairs of sides congruent. We don't need anything else. That's all we actually need. I don't care about the angles right now. Okay, if we can just get the sides congruent, we can use our new postulate, which we just said before. Triangle ABE is congruent to triangle DBC because of, and we can literally just write side, side, side. Okay, it's the side, side, side congruence postulate. But if you just write side, SSS, I know exactly what you mean. Okay. All right. Hopefully that'll get you through the proofs part. The only other thing that they sometimes give you is this. It's going to be the same idea. You're still going to use side, 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 but sometimes they give it to you in coordinates. Okay, they'll give you they'll give you some triangles based on the coordinates. So like 1, 2, 3. Let's do this one. So let's say J is here at -3, -2. K is at 0, -2. And L is at -3, -8. Let's just say it's down here. -3, -8. And you've got this triangle. But then they give you another triangle. Let's say it's out here at 10, 0. So that's R, 10, 0. And 10, -3 will be S. And then T is going to be at 4, 0. So 4, 0. Let's just say it's here. Okay, so they're going to give you coordinates. I didn't draw that so well. I'm sorry. If I had graph paper, that would look a little better. Just trust the values that are there. If you do it on graph paper, it'll be a little bit better. And they're going to ask you, is triangle JKL congruent to triangle JKL? So it's going to be RST. And they're going to ask you to show that. Well, because we have coordinates, we can actually find the lengths of each of these sides. Okay, and you kind of did that in yesterday's homework too when it said to verify all the corresponding parts were the same. You had to do the same basic thing. The only thing about this one is we only really need to do it for the sides. So let's see. This is horizontal. I can just count from 4 to 10. That's 6 units. From 0 down to -3, that's 3 units. And then to do this one, I am going to need to use the distance formula. So if I want ST, I got to use my distance formula. So -3 minus 0 plus 10 minus 4. And we've done this so many times now, hopefully it's not that big a deal. -3 squared is going to be 9. 6 squared is going to be 36. So that's the square root of 45. Square root of 45. And if these two triangles are going to be congruent, then each one of these should match up with the corresponding side from this triangle. So again, I have a horizontal segment here. From -3 to 0 is 3 units. That's a good start. From -3 or -2 down to -8, that's 6 units. That's helpful. And then I got to use the distance formula for K to L. KL is going to be -8 minus -2 squared plus -3 minus 0 squared. -8 minus -2 is the same as -8 plus 2. That's -6 squared plus -3 squared is going to be 9. And check that out. It's going to be exactly the same as what we got over here. So therefore, these two triangles are congruent using side, side, side. So sometimes the distance formula is how you're going to get those lengths to make sure they match up. If we got, 2 here, 6 here, and whatever here, and the 2 doesn't match up with the 3, then that's it. You can stop and just say these triangles are not congruent. Just realize that the 3 matches up here. Because again, think of the rigid motion. This one looks like it's actually rotated somehow to get to this spot here. Okay, so it's not that this 3 has to match up with that 6, obviously. As long as the 3 sides do actually match up, you can justify it with a rigid motion just to be sure. Alright, hopefully that'll help you out. If you have any questions, please post them, and I'll help you out whenever I can and over the weekend. And good luck. Alright, talk to you guys later. Bye.